Hi, Sam Roberts here for ProRaster Scientific. So a few weeks ago I made a video about the GLO-30 DEM data, global 30 metre or 1 arc second digital elevation data that's made available through European Space Agency. And I showed you how to take that data, which comes delivered as a whole series of 1 by 1 degree TIFF files, and put them all together and mask out the ocean and turn them into a digital elevation raster in ProRaster Scientific. So in addition to the elevation data that's shipped, there's also some ancillary data. There's a height error mask, there's an editing mask, there's a water mask, and there's a filling mask. And I promised that I'd show you how to treat that data as well. So, so let's have a look at it. And we'll be looking at this in the context of New Zealand. So here's the New Zealand digital elevation data at 30 metre resolution. This is GLO-30 data. All right, so bring this over here. So remember that the way that we process the DEM data is that firstly we created our raster sources. So so we've got our New Zealand DEM. Actually, I don't even have it at the moment. I've deleted it. But for example, here was a New Caledonia DEM. So we picked up all of the TIFF files in that directory structure, and we looked for a star.dem in this case, which picks out only the DEM TIFF files and differentiates them from all the other TIFF files. That gave us a raster source with a whole bunch of TIFF files in it. We would then go into, we then did the same for the water mask, and this was the New Zealand WBM. This is the water mask, all the WBM files. And we then went into the processing menu. We created a raster mask for the water, and then we did a clip to raster. And then we did a and then we did an export operation out to an MRR file, and we applied some compression properties and got it down to a nice compact and efficient file. So let's have a look at some of the other things. So the next one is the HEM. This is the height error model, error mask. So this is actually floating point data. So it's 32-bit floating point data, and it's the estimated error associated with the data, which they estimate from some other characteristics of the radar returns. And I just want to make one point about this, and that is if you go and look in the, let me dig this out, the manual. So here's the manual, and here's the height error mask, and it says here that it has a value of -32767 in that mask. So any pixel that hasn't been that has been edited or filled, in other words, comes from some other source, that's given a value of -32767, and everything else has got some height error estimate in it. So 1.2 or something like that. So we need to deal with that. I mean, that's essentially a null value that they've embedded into the raster data. So you go into the advanced properties, and in here for the TIFF driver settings, you can specify the null value, and I've set that to -32767. Then what you do is you hit clean and you hit prepare. So that's your cycle. You change the advanced properties, then you clean out all of your cached files, your overviews and your statistics and so forth, and then you hit prepare, and that recomputes all of those with those new settings applied. Then hit OK. If you don't hit OK when you exit the raster source editor, the changes that you made are thrown away. So make sure you hit OK. If you hit the cancel button or you just close the window, it won't save the changes. So with our HEM, we can then go into processing, and we'll do a join operation. So we choose our HEM data, we output it to a new virtual raster that will join all of those tiles together into one raster, and then we can export that raster out to an MRR. Now, and I won't go through this process, but so in this case, I always set the compression output to quality, and then in the advanced settings, with this particular data with the error height, I used decimal point restriction. So I restricted it to 2 floating point decimals. So that's 1 centimeter vertical accuracy, which is more than enough in this case, and that it allows you to compress the data a bit more efficiently. So that's how I exported that data. Let's just see what it looks like. What am I looking for? HEM. Here it is. Make a new algorithm. So here's the HEM data. So you can see there's big gaps in it where the data has actually come from something else, where it's been filled in by some other data, and so they don't have an error estimate. But elsewhere, you get these error estimates, and so where you have houses and trees, you tend to get a higher error, and then in the paddocks, it's a bit lower. But you can see that there's some stripiness in it, so it's not perfect. And here's a big sort of area that's higher than elsewhere for no good reason. But that's your height error data. So looking at something like the water mask and the other masks, just want to show you one thing. So, well, let's go into, say, the fill mask. So these are all the FLM TIFF files. So these have a value between, I don't know, about 1 and 13 or something. So they're essentially a classified raster. And so when we build the overview pyramids for a raster like this, we can't do any averaging or interpolation of data values. You've got to choose a data value from the underlying level for the next level based on, statistics, based on probability. So in the advanced properties for these, I override the field type of the raster and set it to continuous. And then I override this thing called the band value type. And you choose one of these and add it into this list for each band. So we only have one band, and it's got to be unique. So unique indicates that it's classified data, and so when it builds the overview pyramid, it's going to do the right thing. Again, with this stuff, you set those properties, then clean, then prepare, and that will build the overviews correctly. So with this classified data, we want to turn it from this sort of pseudo-classified TIFF file into an actual classified raster. And you do that with the classify operation. So here's a classify operation. So you bring in your raster source. So let's do the fill. So FLM. There's our raster source. You select the field and the band. In this case, only one. And then you set your output raster file name. Your index band data type will be an 8-bit unsigned int. In this case, there's only about a dozen or so classes, so that's more than big enough. And I'm going to define the classification table and the classification data map, the data transform that takes data values and converts them into row indices in the classification table. I'm going to specify them as CSV files. Let's just take a look at what they actually look like. So what are we looking at here? Filling mask, yeah? FLM, yeah, so put those into Notepad. Sorry, while I dig around. Okay, so here is here's the class table. So I have a a label at the top. This is the name of each column, and this will become a band name in the classified raster. And then we have these special IDs, which identify whether or not each column is a special kind of column. In this case, they're all special kinds of column. This is our original class value, this is our label that we want to present to users, and this is the color that we want to use to render the raster. Now, you create these tables using an Excel spreadsheet, and that ships with the product. So you use that as a template, make a copy of it, and the IDs, these special IDs for all of these things are in that spreadsheet, and you just select what you want. The next line is the data type of each column in this table. Again, in the spreadsheet, you just select what you need. And then you have all of the table data. So we have our original class value here, 0, 1, 2, 3, 4, 5, 9, 100, 101, 102, and then the label. So data coming from Raster, SRTM 90 or 30 or 30 plus, and Norway, and so it goes on. And then finally a color. So that's our table. And then we need our data transform. So it's another CSV file. It's a numeric transform where we're just mapping one data value to one zero-based index. And in this case, it's simple, right up to the end here where we're mapping values of 100, 101, and 102, in this case to index 10, 11, and 12. So they're my classification tables, so I put those into here. So filling mask, and here's my filling transform, and then hit OK. And we're going to create a classified raster. I suppose we'll do this. So it'll be FLM. Hit OK. And now that will automatically open, and you'll see here our classified raster. So this is coming from SRTM 30. This is not edited. It's actually amazing how many raster sources they bring into this data. SRTM 90. If you go and look carefully, you can find big sort of anomalous areas where you can tell that they've brought in quite different data to fill some kind of gap. So it's quite interesting going through that. Anyway, so that's your fill mask. What I strongly recommend whenever you create classified rasters like this is that you then go and export them. So export out to an MRR, so that you're working with a virtual raster anymore. So you load up your virtual raster, so this is FLM. It's going to output to this file. And then with settings, what I suggest is I always use quality compression, and in advanced settings, for classified rasters, run length encoding is usually a very good strategy. So we take each tile, we do run length encoding on that tile, and then we compress that data, and that's what then goes out and is stored in the file. And then that process is reversed when you read the data back in. So that's my suggestion for classified data, and then hit OK, and out it will go. We won't go through that process. So let's have a look at some of the others. So we have the water body mask and the edit mask. Let me just bring those into Notepad. So here's our water body mask. It's only 4 classes in that. Water, ocean, no water, ocean, lake and river. And here's our transform, very, very simple, just numeric. With our editing, you can see that there's only 14 classes, and it identifies where all these pixels come from and how they've been edited. And again, the edit mask transform, there it is, will be very simple, just a numeric transform, and in this case mapping from exactly the same value to exactly the same value. So you go through that same process, and you can produce all of your masked rasters. So let's just have a quick look. So here's our terrain raster. So here's the edit mask. So you can see that we have our ocean pixels, not edited, infill, all this blue is not edited, lakes, rivers, and then other pixels that are infill and various other smoothed and so forth. So that's our edited data, our edited mask. Here's our filling mask that we just made before. Should probably have this over here a bit. So here's our fill mask. So much filled data. All these yellow pixels are coming from SRTM30 instead of World DEM. Well, let me be clear about it. It's all coming from World DEM, but and these masks are actually derived from World DEM. So it's the way that World DEM has processed the original data, and that was at a higher resolution to this GLO-30 data. But they've transferred those masks across. Water we've seen before, and we've seen the height error mask. So that's how to deal with these classified rasters in ProRaster Scientific. So take them from a bunch of TIFF files which are difficult to deal with, turn them into a true classified raster using the classify operation. It's a virtual raster, and then do an export of that virtual raster out to an MRR, which will crystallize that data, turn it into a real raster, which you can use thereafter for all time. And to just give you a bit of a comparison, so the original data is like 7 or 8, I think it's about 8 gigabytes, and here's our final grids, all of our grids, including the error model grid, and we've got 839 megabytes of MRR files there. Much easier to work with and much easier to store. So thanks for watching.